Hi, hello, Miss Kelly. This is my second exam honors video. This time I will be covering the topic of partial derivatives and how they're used in physics. So, when you think of physics and electromagnetism, there's a concept called potential energy. Not potential energy like gravitational potential energy, it's electric potential, which is described by an influence, you could think of it, by an electric field. So, for example, here you have two plates, and say this plate has a high potential and this plate has a low potential, then there's like an electric field pointing from high to low. And then this is described by the equation of the change in voltage is equal to the negative value of the derivative of the dot products of the electric field vector and the distance covered. So this would be, in this case, this would be dl, right? Now, this only works when you have one directional field, but what happens when you have a field that changes at all points in all three dimensions? Well, you have to take partial derivatives to find it. So you start summing up the portions, and then you start using the ijk's instead of the separate equations. So here I have a problem. We're giving an equation in terms of x, y, and z for the values of the voltage at any given point in space. Now, this was one of the problems I had on my exam. It took me a while. And basically, the way you go about these problems is you take the partial derivative with respect to each variable to find like the horizontal, the vertical, and the in and out component of electric field. So that's what we're gonna do. It's asking to find it at 462. So I'm just gonna keep this up here, 462, 0.462, and then we're just gonna go straight into it. So first you have to find the partial derivative with respect to x. So e with the x component is equal to the partial derivative with respect to x of v x, y, z. And this is equal to 10x, y, z to the third minus 2y, 3 to the third, z squared. And then to find the x component at 0.462, you just plug in for ex and 462, and then log calculations aside, you get a final value of 192 volts per meter, which checks out with our original equation. This is in terms of volts, this is in newtons per unit charge, and then this is length, which is just meters, measured in meters. So when you pass over the value for E is measured in volts per meter. So that's our first equation, and this is in the negative I hat direction. So you do the same for the y component. The y is equal to the partial derivative of y of the voltage equation, and which is equal to, 1 second here, so 5x squared z to the third minus 6xy squared z squared in the negative j hat direction. So when you get the partial derivative of y and you check for 0.462, you get 2,816 volts per meter in the positive j hat direction. And I'll just avoid the third partial derivative. It's just, we will find that the z component of the electric field is 1,152 volts per meter in the positive k hat direction. So knowing all these components, we're asked to find the magnitude. So it's the same way you would find any other magnitude for any vector. So you just do Pythagorean theorem. So we take our values, we square them and take the square root of each. And we're just gonna do that real quick. I'm gonna do this with blue marker. So the magnitude of the electric field at point 462 is equal to the square root of 2 volts per meter squared plus 2,816 volts per meter squared plus 1,502 volts per meter squared. Take the square root of all of that, add all that up, and the final value is, I need a calculator. Thank you. The final value of all of that is, 1 second, Miss Kelly. It's gonna take me a bit. And the magnitude of the magnetic field is 3,408.5 volts per meter. So that is how you use partial derivatives in the context of physics concepts. It's pretty much the same thing, you just use it to find other stuff with more meaning than in Calc 3. In Calc 3 it's just the partial derivative, it's just the rate of change within a line. Here it's actually, it can mean other stuff when talking about electric fields. It can mean the change in potential across a certain axis. Yeah, thank you.